So let's talk a little bit about how a visualization can occur. Oftentimes in science, we go with a problem, we think of a linear solution to that problem, and then we present those results. It's a very unidirectional method of thinking of your problem. One thing I'd like to introduce to everyone is how designers think about approaching a problem. And so this is called the double diamond method. This is a graphic that's taken from the Design Council of the UK. And the idea here, especially, and that's particularly relevant to serendipitous science or archival science, where you don't necessarily know what you're looking for, is you start by talking about what you think the problem is, but then you expand that definition. You try to think of all the possible problems that could be related to whatever data set or whatever challenge that you've been given. So you try to discover some insight into the problem, and then at that point, then you focus down into the problem itself, right? So part of the challenge is choosing the problem you want to attack. And then at that point, this is the point where normally we think of science actually coming in, but scientists start here. You think of possible ways to try to solve that problem. And then you choose the one that seems to be most likely, and then you converge. But the big thing I want to point about this method is that it is not unidirectional. You go back and forth, right? For instance, in the discovery to the problem, or the discovery of what might be related to the problem, you might go back and actually pose a completely different problem. Maybe this data set, or maybe what you're collecting, isn't actually the most relevant or useful problem that you should be collecting or trying to approach, right? So you should be going ping-ponging back and forth on this diagram. Now, the final point I want to make before we start talking about individual visualizations is how do actually humans interact with your visualization? Because at the end of the day, a visualization is a tool for which a human will try to interpret what's happening within a data set or et cetera. So there's a fantastic book that I'd recommend if you're interested in visualization or the way humans interact in general, that I strongly recommend, called The Design of Everyday Things. It's by Don Norman. He's most famously known for coining the term a Norman door, because of course you name things after yourself. A Norman door is a door where you have a handle that expects you to push on a door, but in reality the door is a pull one. Right, so the notion there is that there is some information encoded in the design of the object that tells you what you should be doing about it, or doing with it. And this is particularly important when it comes to understanding how to design a visualization. So let's talk about how do humans actually interact with your visualization. The first level which humans interact with visualizations, or any sort of interface, is mapping. Right? One of the things that we're really good at doing in our own brains is trying to map things, right? We see a set of knobs or a set of switches, let's say these switches. This is a perfect example of unfortunately not a great mapping. A good example of a mapping would be if the switches were connected or close to the lights that they were going to turn on. An example of a bad mapping would be, for instance, a stove. How many of you guys have turned on the wrong burner millions of times, even though you've owned the stove for years at this point? It's because your brain is still not connecting. There's not an inherent mapping to that. So fixed positional placement interprets how you interpret what you should be doing with that, or how you should interpret that particular design. The second thing is feedback. So if you have an object or a button and you press it, and it beeps, it tells you, it gives you some sort of feedback signal that you've done something to it, that it is now, accepted your response. A good example of where this, fails miserably is how many of you guys have pressed a button at a crosswalk and just kept on pressing it 5 million times because you don't see a light go off and you expect it to continue? So that's an example of bad feedback, where you don't actually have any indication that what you're supposed to be getting is what's supposed to be happening is something that is in play. The third one is conceptual models. So if you don't have an easy way of mapping it to a space that we understand, if you don't have an easy way of giving some form of feedback, the next one that you can rely on is some sort of conceptual model that humans have inherent or have been learning. Right? A good example of a conceptual model would be the Cartesian plane. right? We all know that, if you place an object or a point on a Cartesian plane, it represents, something about the distance between the plane, or it represents something about the position between whatever points that whatever points you're saying, right? This is a conceptual model that humans have learned, or scientists in general have learned, and that's something that we can use to our advantage, right? Anytime you look at a graph, you can interpret what it's supposed to be saying, if it's supposed to be rising or falling, etc., based on what you know about Cartesian planes. Same thing's true about pie charts or any of these kind of diagrams. The conceptual model helps the human understand, even if it's not precisely correct. Right? It's a filter through which to look at it. And the final thing that I want to, that if we don't have any way of creating the first three, let's say that there's no easy way of building a conceptual model, you have no feedback and you have no mapping, cultural conventions. Right, a good example of a cultural convention that fails miserably at many locations is what side of the road do you walk on, or what side of the sidewalk do you walk on, right? There's no particular reason that should be one way or the other. There's no mapping, there's no inherent feedback on a lot of roads, unless you're like really in the middle of traffic, and in which case the feedback's really bad because you'll crash into somebody. And there's no inherent conceptual model, or there are, in this case, diverging conceptual models. But the challenge with, so cultural conventions can be incredibly powerful, but they can also be incredibly misleading. So you have to be careful with trying to use a cultural convention to try to convey something. And a good example of this is asking this question. By show of hands, how many people think this line is going up? Pretty much everyone. There's a couple people who are a little resistant because they know I'm probably going to tell them that that's not inherently true, because it's not inherently true, right? The vast majority of people in this room will say that this line is going up because we have we're using a language system that goes from left to right. If the same question was asked with an Arabic-speaking audience or a Hebrew-speaking audience, they would say the exact opposite, that this line is going down. And so one needs to be very careful about how they use cultural conceptions in the way that they interpret the data. And that's not to say that you don't want to use them. It's that you need to know what your audience, if the audience is you, then this is fantastic, right? If the audience is people that think in that same way, this is fantastic. But you have to remember that this is a filter through which people look at their visualizations. Okay, so now we've gotten through a bunch of the preface. By the way, does anyone have any questions at this point, or things that they want to poke at, or vehemently disagree with me on?
Well, I've never heard that in Arabic-speaking world that graphs go reversed.
They don't, because that's right? And this is an ongoing challenge. It's because the Cartesian plane, the way that we teach it, is defined such that positive is on the right-hand side. But in a good example of where this is not the case is look at actually photographers who are Arabic-speaking. An example of this is leading lines. In general, when you're a photographer and then you want to create a sense of movement in a picture, you usually have a leading line that goes up to the right. In a lot of photos that are taken from Arabic-speaking and Hebrew-speaking peoples, the leading lines will actually go to the left. Because again, there is something deeper about language than about cultural convention, right? The way that you interpret, even written language is built further into you than just teaching somebody that it's supposed to go right or left. Other questions? All right. So let's go back to the basics and talk about how do we actually encode information in visual forms. So there's a variety of different ways to do it. So we're going to go through these. So first off, you can represent information in position. So for instance, a scatter plot is a perfect example of representing information in position. The location of the point on the scatter plot tells you precisely, or it tells you the relative distance between any of the points, tells you something about the distribution, tells you about how proximal things tend to be. And so this is fantastic for representing two non-categorical or two very numerical variables very easily. And it also has, as you mentioned, strong cultural convention, right? Most of us learn the Cartesian plane. Most of us have a sense that, on the right-hand side of the x-axis, things go up, right? So that's something that you can use to your advantage. But the other thing I want to point out is that position can be more than just precise numerical values. We know, for instance, right off the bat, by looking at this particular plot, these points have nothing to do with these points. We're actually separating them by position for a categorical purpose in this case. Right? Position now in this point is both categorical, and then within each frame is telling us something numerical. Part of the reason I actually put this particular plot is an example of where visualization helps, where some sort of statistical model doesn't. Can anyone tell me what is the same about every single one of these distributions?
They're not random.
They're not random. No, they're random. Like this is a normally random two-dimensional distribution. I'm sorry?
Total variance or something.
Total variance. So they have the exact same variance, they have the exact same mean, and exact same variance and standard deviation. Right. So if you did your 5 points and also x and y range, if you did your standard five value statistical test or statistical summary, all of these distributions in the x-axis would look the exact same. And importantly, in the bottom row, these are seven different distributions that also all have the exact same correlation coefficient. Right? There's information in there that unless you had visualized or unless you'd used some other higher order test, you wouldn't have gotten.
That's interesting. What's the reference for that figure?
This is actually from Creative Commons. So you can actually pick up the, what this was supposed to be representing in this case was the correlation coefficient. So it's on the correlation coefficient, but it's completely open source.
You can find the bottom one called Datasaurus. The one the reference.
Right, yes. Yeah. There's another one that's actually an animated one where it just changes the distribution into a bunch of different things where in that case, the correlation coefficient, the mean, and the standard deviation all are the same. Which is a fantastic example of how sometimes these parameters aren't enough. So the next one I want to talk about is size. So area can be a fantastic indicator of magnitude. Right? This is something that we as humans are very well adapted to do. Right? The area that something takes up in your field of vision tells you about if something is bigger or closer than something else. And we can understand that very easily. So for instance, this is taken from a WHO report on the status of the AIDS epidemic from 2018. And from this, we can say that we know only 40% of this graph, just by chance, this is the fraction of people that know about their HIV status. This is a good example of, for instance, what is the fraction of people, for instance, in Asia versus sub-Saharan Africa that are HIV positive or have obtained HIV. And you can very easily, just by your eye, be able to compare things. That is what area is particularly good for. It doesn't give you a precise, you can't read off that this is exactly a certain amount of area, but you can tell relatively from other things how it fits within that. So it's a very easy way of comparing elements in a figure. A good example of this is a pie chart. In this case, this is my favorite pie chart because it's a pie chart of pies. Shape's another good one. So shape is particularly useful to encode categorical information. So in this particular case, this is a standard flow chart where, because of cultural conventions or some form of mapping, we have a sense, if you read flowcharts regularly, that these diamonds are supposed to be decision points or questions that you ask. These blocks are supposed to be nodes in which you follow through. The sort of curved blocks are the ones where you start and end. Right? There are strong cultural conventions that are associated with that. So you look at this, you know where to start. You know what each of these elements somehow means. And then, of course, my favorite flowchart. I might be a little too old for a lot of people in this room, but moving on. This is the one that a lot of people don't pay too much attention to. Thickness. It's highly underutilized, but it can be very effective. A good example of where this is effective is the streetcar map of Toronto. In this case, you know just by looking at the figure, which are the major lines and which are the minor lines, right? Which ones are the subways, which ones are not. This is also very, very good to be able to filter out or allow people to filter out, or you to filter out, what is a reference point on the data versus what is the actual data itself. Right, so using thickness to your advantage allows you to categorize things visually.
Why isn't it just part of shapes?
Because thickness actually, so it is related to shape, but shape doesn't, there's something different between a shape, a specific figure, and something that has direction, right? And so I'm trying to separate out the notion of lines being different than just blocks.
I guess this is also of size too.
It is size related, yes, yeah. But it is visually something that is different. That's what I'm trying to get at, in the way we understand it and we can process it. But that's a fantastic question. Color. So one of the great things about human beings is that we have the ability to distinguish relatively between different colors very well. There was a little quiz that was going around the internet about a year or two ago where people had to separate out or try to order things in terms of what color they are, the bluest to the reddest. And there was like 100 different patches. And people in general would only get, I've ordered 10 of those out of the 100 in the wrong position relatively. You know, this is a testament to how well the human eye can actually distinguish relative differences between colors. It is incredibly powerful. So what it allows you to do is allows you to encode some sort of magnitude information with basic comparative properties, right? If you want to be able to compare things that are high or low, a good example of this are contour maps, right? Where you want to say, you know, where is the highest peak of the mountain, where is the lowest valley in the mountain? Color is a fantastic example of how to encode that. But the second thing I'd like to point out is that it has the potential to encode large ranges of variation. Right? Let's say that you have a cliff, an actual physical cliff where there's some variation on the bottom and some variation on the top. There is not a built-in human understanding of what color should go with what value. So you can actually bridge those two and have a lot of variation where you need it and not much variation where you don't need it. Right? There's not a direct mapping to the value that you use and the color that it appears as. So that's a powerful thing. It's often seen as a detriment of color, but it can be a powerful thing because what you care about is comparing variations. So here's an example from the WF in terms of trends of polar bear subpopulations. In this case, just as an example of how we don't actually have distinct numerical associations with color, in this case, they're being used as categorical information, right? So we have chosen in this case just 4 different colors, and these are easy ways of being able to distinguish between categories. Opacity. So this is color related, but it's again something that is interpreted slightly differently than color. So it's often used in conjunction with color, and it provides accrued information of magnitude. Right? The darker something is, or the less that's underlaying it goes through, the higher the magnitude of whatever effect that you're looking at. A good example of this are radar maps. So this is a radar map, not obviously of yesterday, it is way too light. But you can see where the darker shades indicate something of greater magnitude happening here, whereas what's lighter. And what's particularly useful about this is that it allows you to use more than one element. It conveys more information in there, right? Because now you can also see as a reference below what's going on. A good example of how this is used, so encyclopedias, especially from the 70s and 80s, would often have inlays where there were transparencies, and you'd overlay a bunch of inlays to see some effect, oftentimes on maps or a map of the human body. And that's a good use of using opacity in that case to actually be able to convey different categorical information. Right? Each of those overlays would be a different category of thing. For instance, on the human body, it'd be a different the nervous system or the digestive system. So a good use of of how opacity can be helpful. So now these are the basic elements that you can play with, and these are things that have different ways that we interpret them as human beings. So how do we actually use these elements? So one of the things that I'd like to encourage everyone to do is to be unconstrained by legacy. Right, so this is a fantastic example from Tufte's The Visual Display of Quantitative Information. And this is your scatter plot. This is a scatter plot that would probably be marked very poorly by my grade 10 science teacher because it doesn't have axes labels and blah, 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 blah. But it's a scatter plot nonetheless. What if we wanted to convey a little more information on the scatter plot? For instance, something that's often useful for a bivariate data is figuring out what the range is. What if we just made the axes encode information about the range? We now actually have more information about that data set without having to say anything greater or having to put more ink on the paper, clutter the figure anymore. Maybe instead, we want to be able to say be able to indicate where every single point is. And this has the added benefit of now, just visually, you have two one-dimensional histograms as well. Right? You can see the distribution of the plots of the points on the bottom and the distribution of the points on the y-axis. And you haven't added much more. There's not a great deal more clutter that you've done to that. It's not like you've taken up this space and put a new histogram over there. Right? You're using the elements that are already there, in this case, positional and thickness-based elements, to tell you something more about that data. So I strongly recommend being unconstrained by these legacies. Something else that we often fixate on as scientists is this need, this obsessive need to show our raw data. The thing that I posit to you is that all data is going through some sort of filter. What you consider raw data is likely not raw data. It has likely been processed through some other filter to get there. And it's probably giving you some overconfidence in just how raw that data is. But distributions often encode a great deal of information. So here's an example actually from my own thesis work, where in this example, these are all the stars in a certain region of the galaxy where I think there's supposed to be something happening. Right? I plotted all the stars naturally to try to figure out if something was happening there. And if you didn't even have the circles there, there would be nothing that looked remotely interesting or useful. And that is because the information in this particular set of data was not in the individual positions of these stars. The information in this data was actually in the difference between the positions or the density of these stars at a certain density threshold. That's not easy to convey, right? You're not going to be able to see that from a scatter plot. But if I chose this is the exact same data, but if I chose a different metric, I don't know where any individual raw point is in this, but now I can see where the information is contained there. Right, so don't hold this notion of always showing the exact raw data to be, or whatever you call the raw data, to be gospel. Right? There's often times where that's going to just hinder you from where the information in that data set actually lies. Yep.
There are actually some journals who recommend that you use as least transformed data as possible.
Mm-hmm. There certainly are. I would posit that that is a misguiding statement. Right? It's the same level of, it's one of these things that people often have kind of taken up the arms to because of how badly people have gone down the other direction. A good example of this is the whole fight over p-values in a lot of, especially the biology journals, where a lot of, the American Statistical Association actually came out saying don't use p-values anymore. It's still a useful technique, but you have to know when it's supposed to be used. And so that's what I would say about in terms of this argument over raw data. What you want to do is you want to show the data in such a way that actually shows you where the maximum information is. Sometimes that's going to be in a very, very complex way. Like many people that are just down the street are trying to figure out from the cosmic microwave background where these B modes are, and that's a very faint signal. You can't do it without processing the data in a very unintuitive way. Should they not be doing their science, right? Like that's a reasonable question to ask. And what I would say to that is, just to come for full circle, is ask what they mean by raw data, right? Ask what they mean by processing it, right? Because at the end of the day, if you're trying to answer a very fixed question, you could probably concisely say why this transformation is relevant, why this transformation is important. Does that answer your question?
Yeah.
Well, I think there's this tension with cultural conventions, right?
Yeah.
Journals have specific guidelines, and in fact, fields do. Like astronomy says, "Oh, plots should always look this way."
Exactly. Yeah.
If they don't look that way, I'm going to go like, "Who made this?"
Yeah. Yeah.
I don't have to pay attention.
One of the things that I've been finding, though, is more and more journals, especially talking to editors in astronomy, and a lot of other journals are starting to be willing to talk about how we actually present data and start to see their faults. In some case, these things are being pushed by the what's known as the reproducibility crisis, where things that were thought to be gold standard weren't necessarily reproducible. But in some cases, it's just data is getting more complex. And trying to figure out how best to present that. So this is a conversation we need to be having with our journal editors, because the state of science is going to be, it's going to be driven by how, who gatekeeps the information, who keeps the visuals, etc. But yeah, no, that's a completely valid point and important. Other questions at the moment? All right. One thing I did want to point out, these slides I believe will be available afterwards, so the links in it will be available. But a good thing to look at is, in terms of the way that you can actually try to go through a data set and try to explore it, is Nathan Yao, who runs the Flowing Data blog. He took one single data set and tried to visualize it in 25 completely different ways. And it's instructive and useful to just take a look at the different ways that he tried to plot the exact same data. It's a nice little challenge for yourself. If you have a data set that you're working on, try to push it in a different direction that you didn't think it would be the case, right? So going out from anywhere from, ordering the data and actually trying to understand patterns in the ordered data versus, individual, in this case it's life expectancies, so trying to see trends in life expectancy per country ordered around. Right, so there's a lot of different ways that exact same data set, which is not a very high dimensional data set, can be understood and can tell you something different about that data. So worth just taking a look at. This is a little bit of a pet peeve of mine, so I will try to refrain from ranting on this, but typography is a good example of where something can be seen as benign, but it can actually be very effective at conveying some form of information, in this case, categorical information. So an organization that does this particularly well is the National Geographic Mapping Cartography Division. So they've got a very strict style guide for what features are at what type of typography and when it's used where. And then what that means is that they both used it as a form of visual separation, and it's also developed its own cultural connotation. Whereas if you look at this particular regional map from, this is the United States map from the National Geographic Society, you can right off the bat tell what are major features, what are minor features, what are bigger towns, what are smaller towns. And this is through a very purposeful use of typography. So it's just something to keep in mind, right? Letters and text and language has meaning intrinsic to human beings. You don't read a word as individual letters or individual strokes, you read it as a word. So that can convey some information that won't necessarily show up as a bunch, as points or as thickness or as lines or as blocks. So use that to your advantage. Right? Oftentimes the best way to actually make a plot or a visualization better for a journal because it doesn't represent something is just label the thing. Right? That goes a long way. So let's talk a little bit about some of the available tools in the last few minutes. So I'm going to be going from tools that I know the best to the ones that are, I'm a little more shady on, but I'd like to give you a bit of a wide gamut of modern tools that people use. And so the first one that I actually do most of my plotting in, this is a figure that I made for a paper about 4 or 5 years ago, is Matplotlib. So it is the interfacing language of it is Python. You can both use it in a scripted or interactive environment. And the use case for this is really complex multi-mode visualizations. That's what it excels at. You can also make highly interactive visualizations here, and it can be highly extendable, right? For instance, let's say that you wanted a plot that shows the map in a certain projection, and then it has like a scatter plot that is blowing out of it. You can do that through all the extensions that are already built in to Matplotlib or easily accessible. An example of this is all just one script that did this entire plot, right? I didn't do any fancy things in Illustrator here. But we have, completely independent scatter plots. We have a completely independent, categorical color bar going on here, all done with one thing because it's very rich in that ability. How many of you guys actually use Python in this group? A few of you. How many of you guys use R? JavaScript? Any other languages? MATLAB, C. You use C.
Why don't plot it?
All right, so there's something for everyone here. One of the points as we're going through this that I want to make is that separating out defaults from the underlying power of the mechanism, right? Matplotlib, by default, it's getting less ugly, but by default, it is ugly, right? It doesn't actually do exactly what you want it to do, and it makes for some, shall we say, shabby-looking plots, versus a lot of what you can do with it is hidden deep in that power, deep within the system. And what it allows you to do is, put in a great deal of different axes, lets you transform these axes, create, customize all of this together. So both of these are using the exact same version of Matplotlib, but one is just, defaulting to the defaults, and one is trying to leverage some more of that power.
How long it took you to produce that one?
To do this one?
Yeah.
Probably a week. Yeah. So for those of you who are regularly plotting larger data sets, what I'd recommend in using Python to do it is something called data shader. So this one, for instance, this is every single census point in the US Census from, I believe, 2010. So over 300 million points, all plotted in a single file, or a single, I believe this is an SVG. And so data shader is fantastic for larger data sets. It's high performance rendering. We'll actually use OpenGL to do the rendering for you. So if you want quick histograms, for instance, of billions of points, this is the tool to be using. Right, Matplotlib is not the tool to be using because every point in there is going to be its own object and take, some number of K in memory, and then your system will blow up. And that's not a good thing. For those of you who are in R, I'm sure this is now default to a lot of people, but ggplot too. So this is not the out-of-the-box R plotting tool. There are built-in R plotting tools, but I wouldn't recommend using them right off the bat. But primarily, it's scripted. For those of you, so ggplot, the name comes from a textbook called The Grammar of Graphics. That's where the GG is. And the notion here is you have data. The basic idea of this textbook, or this piece of Grammar of Graphics is, you have data, you do some sort of visual transformation to it, you get a plot. So that's how this thing is structured, where you have the data, there's some sort of aesthetic transformation that's done to it, and then that turns into a plot. So it's particularly useful with categorical data. There's a lot of built-in categorical data methods in it. It's a very high-level syntax. It's not the kind of thing where you want to tell it exactly what point you want to be plotting at that exact location in a figure. It's better for, hey, I want a box plot of X, and I want that to categorize things based on X and Y, right? It's fantastic for that.